We continue with our story about the load flow method. As you know, the load flow is a bread and butter for any power system engineer. You cannot solve any power system problem without load flow being a part of it, because it gives you the pulse of the system. It tells you what are these four vital parameters in electrical engineering, namely real power injected, injected reactive power, voltage magnitude and angle delta. We have just finished Gauss-Seidel last time. Today we are starting the most important method, very widely used, Newton-Raphson load flow method. This Newton is the same Newton, that Apple one, and it is a numerical technique, as I told you, it is nothing to do with electrical engineering. Those of you who have done a course in numerical analysis in your undergraduate or anywhere, a book by like Hildebrand or Iyengar and Jain and so on, you must have read a Newton method. It is nothing but a numerical technique to solve any nonlinear algebraic equations, and as you all know by now that your load flow equations are nothing but nonlinear algebraic equations. Now, NR, as it is briefly called or it is abbreviated, is a very powerful method of solving nonlinear algebraic equations. It is very fast, convergence is very fast, and not only that, convergence is assured, it is guaranteed. There is no way that method won't converge once you use Newton-Raphson. It is a very practical method. System size can be anything, let it be 1000 bus, let it be whole country of size of India or former USSR or US, whatever, it will give you solution. Only problem is, as I told you, every time there is a plus and minus in anything that you do in life. The minus point of Newton-Raphson method is you need a large memory. In olden days, when memory was an issue, now it is no longer an issue. We used to use compact storage scheme, which used to tell us how to solve such a problem using Newton-Raphson without crossing the memory limit. Anyway, now you do not have to worry, as your most powerful computers are available. Let us consider a set of nonlinear algebraic equations. Writing in a mathematical form, Fi x1 up to xn equal to 0 for all I varying from 1 to n. This is a nonlinear algebraic equation. As I have been repeatedly telling you earlier on, when you solve any numerical technique, you have iteratively, that is, you have to assume an initial solution. An assumption of an initial solution, more intelligently you do, less time it will take for convergence. There where you are, as an engineer, your all past experience, your knowledge will come to your rescue, because you know your system so well, you know what is the starting point. In fact, if it is a daily problem, daily solution, last solution could become a starting point for the next solution. However, if you assume that you do not know anything about the system, it is an entirely new system and you are an entirely new person, first day in the job, you can always assume x10 to xn0 whatever values, and luckily Newton-Raphson method is not sensitive to the starting solution. Gauss-Seidel method was, but naturally since you are assuming initial solution, it will not give you a final solution. Otherwise there is something wrong, otherwise you are knowing the solution. You are not a god, you are a human being. So whatever initial solution you assume, that will not necessarily give you the final solution, because it is a numerical technique. There ought to be an iterations, it is an iterative process. So let delta x10, delta xn0 be the corrections, which when added to x10 will give you next estimate of the variable. Solve it till you get convergence criterion satisfied. Let us see, let us proceed further. Now these things are called corrections. How do you find out corrections? Unless until you find out corrections, how do you add? So next step is substitute x1 by x1 0 delta x1 0 and so on is equal to 0 for all I. Inverted A is for all. This is nothing but a Taylor series expansion. Now we are going to use the first term, the second term is first derivative plus HOT is higher order terms. Now in practice you can almost always neglect higher order terms to make your life little comfortable. Now I can write that Taylor series expansion in a form of a matrix f1 0 fn 0 plus del f1 del x1 0 and so on. This 0 means these derivatives are evaluated at x1 0. In fact, this only means del f1 del x1 evaluated at x1 is equal to x1 0. That is all. To simplify this, I am writing this superscript 0. Delta x1 0 up to del xn is equal to nearly equal to 0. Why nearly? We have ignored those higher order terms. If you want to write in a compact form rather than carrying such a big matrix equation, f0 j0 delta x0 nearly equal to 0. This j0 is called Jacobian matrix. What is the Jacobian matrix? Jacobian matrix is that matrix whose each element is first order derivative. If it becomes a second order derivative, it is called Hessian matrix, which fortunately or unfortunately we have ignored. So now I can write further f0 is equal to minus j0 delta x0, and this delta x0 we have to find out. So it needs an inversion of Jacobian matrix. This is another negative point of this method. In Gauss-Seidel we didn't have to use any inversion. It was straightforward, most easy method to understand. Even an ordinary person can solve using Gauss-Seidel. That's just one equation, as we have seen. Here you have got to invert this matrix in order to get the corrections. However, all of you may be aware, if you have done your numerical analysis course, there is a method called triangularization and back substitution. It only means you have to create all 0 and then xn can be immediately found out, substitute xn here, find out xn minus 1, substitute xn minus 1, find out xn minus 2, back substitution. This is called triangularization and back substitution. The details of this is given in appendix C in your textbook. So you can go to the appendix C. There is a solved example given there, 3 by 3 matrix, which you can easily solve otherwise also. Any 3 by 3 matrix, I think even calculator can give you a solution if it is a programmable. If it is a non-programmable, well, you can solve it. After all, you have to find out cofactors and things, determinant and things like that. Then now we have got an updated value of x. x1 is equal to x0 plus delta x0. This is an updated value. Likewise, in general, you will have xr plus 1 is equal to xr plus delta xr in general. Now, how long you are going to continue with iterations? As I have been repeatedly telling you in earlier lectures, any numerical technique, not only you have to assume initial solution, you have to devise a criterion which will help you to stop. You can't go on doing it till eternity, that means Qayamat. So you have to stop it somewhere, and this stopping criterion is given here. Iterations continue till this becomes less than epsilon, where epsilon is nothing but a specified value for all I. Again, this depends on you, how accurate solution you want. Is this load flow for planning purposes? Is this load flow for real time operation or online control, or it's just a normal load flow. It depends on that what accuracy you want. In our algorithm, now we come to the proper. So far we have been talking about mathematics. Now let us talk of electrical engineering or power systems. For load flow studies, you are aware of these two equations, Pi and Qi. These are called SLFE. Let's say this Pi is a function of x, Qi is a function of x, where x is this delta and V. Why I am doing this? I am assuming that all buses are PQ buses except one. There has to be a slack bus in a load flow problem, and I have also told you why there should be a slack bus. It is a slack bus which does many jobs like supplying the rest of the losses at the end of the solution. It is a reference bus because the deltas of rest of the buses are referred to the angle of a slack bus, which is normally assumed 0. Again, a slack bus is normally given number 1. Without loss of generality, you can always give it any number if you are so fussy about it. Some books also give, or some experts, nth bus also. Now, let Pi is scheduled or scheduled or Qi is scheduled, they are given to you on all PQ buses. What is the definition of PQ bus? Where P and Q are given to you. They are scheduled. Bus, using your initial solution, you can always calculate Pi and Qi. Now, these Pi and Qi which are calculated should be equal to scheduled values. If you want, you can write here calculated also. Now, if it is 0, that is an ideal condition. That means your solution is perfect. You do not have to worry. But as you know, unless until you know a solution, you are not God. You can't assume a solution which is a final solution. So, there has to be delta Px and delta Qx. They are called residuals, mismatch factor. So many names given in the literature. And this mismatch factor or residuals, this is a Jacobian and these are the corrections. You have assumed certain delta 0, you have assumed certain V0. Now, this has to be corrected in every iteration, updated, modified, so that we march further towards our goal. What is our goal? Goal is to achieve a converged solution, the final solution, the correct solution. Now, this Jacobian is known to you because this can be evaluated at trial values at x is equal to x0 or p is equal to p0 or q is equal to q0. And J is also sparse like your Y bus. You must have been told by your teacher or you must have read in your books that Y bus is a sparse matrix. Today this class is not that sparse, it is fairly full. But normally when my only MTech students are there, the class is hardly full. That is called Y bus. Today it is Z bus because all elements are full, available. This Y bus is a sparse matrix and that is why we prefer Y bus for load flow studies, because you do not have to store zeros and hence storage requirement. Further, Y bus has certain other qualities, namely the build up of Y bus is easy by following simple rules which you have been told by your teachers, and even modification of Y bus is easy. So, building up a Y bus is easy, modification of Y bus is easy, it is sparse. That is the reason why this is a very important question normally asked in interviews in engineering services or even IS, why Y bus is preferred for load flow studies. This is the reason. Similarly, J bus is also, the Jacobian is also equally sparse. So, this J is sparse. Now, for each PQ bus you will have 2 rows in Jacobian. For each PV bus you have only 1 row, that is delta row. Why? Voltage is already given to you. So, PV bus contributes only 1 additional row, whereas PQ bus contributes 2 rows. Now, we come to the iterative algorithm. Assume V and delta. Since you are solving a power system problem, you know jolly well that voltages in power system have got to be close to 1 per unit. 0.95 per unit to 1.05 per unit. That is the range in which voltage should vary. Forget about India where it can be minus infinity to plus infinity as I normally say, but that should not be the case. So, in case you are not sure how to assume the initial values of V or delta, you are always welcome to use flat voltage start. The flat voltage start means 1 plus j 0 or 1 angle 0, and you are likely to be close to the final solution. Now certain times it is always better to compute SLFE in rectangular coordinates and not in a polar coordinates. Why? Polar coordinates means you have a non-linear terms, sine and cosine, which takes longer time to get computed. So it is always better to convert SLFE equations in rectangular coordinates. How do you do that? Let EIR, the real value of the voltage, be VIR cosine delta IR, and FIR, the imaginary part of the voltage, is VIR sine delta IR. That means I am assuming V is equal to E plus JF, and V is V angle delta, and that is how I am writing this. GIK, the conductance, the real part of Y bus, is YIK cosine theta IK. Please remember, theta IK is close to 90 degrees because the resistance is very small. In any well behaved power system, in any normal power system, R by X ratio is ought to be very small. X is roughly 10 times. If it is not, then you are solving an ill conditioned system where R becomes comparable to X, and still you can solve load flow because certain systems are ill conditioned, but the Newton-Raphson method will always give you an answer even if it is ill conditioned system, which is not guaranteed with Gauss-Seidel method. So, BIK susceptance is YIK sine theta IK. Now, I am substituting these rectangular variables, and this is the final equations obtained for SLFE using rectangular coordinates. So, you can see sine and cosines have vanished. So, this way you will get a quicker computation of P's and Q's. You need not copy them, they are given in your textbook, whichever textbook you may be using. All textbooks have to give this. Now, as I again ask you and talk to you, we have to stop somewhere in any numerical analysis. How do you stop here? These residuals should be less than epsilon. They won't become exact 0. Don't expect that to happen. Even if you solve x0 is x square is equal to 4 by numerical analysis, by assuming x is equal to 2.1, you may not get 2 answer in 2-3 iterations. You may have to go for some iterations. But if you are happy with 2.0001, you may get it in couple of iterations, which is as good as answer 2. So, here this epsilon, how do you assume? That depends on the accuracy you want. It can be 10 raised to power minus 4, it can be 10 raised to power minus 8, it can be even 10 raised to power minus 2. So, it all depends on you, the designer, the analyst, the expert, the power system engineer. You may have to work in load dispatch center, you may be going to power grid, you may be going to BHEL, NTPC, NHPC, Central Electricity Authority, or Tata Electric companies or any private companies. You will have to solve load flow again and again, because that's, as I said, is your bread and butter. Calculate finally what is the outcome of a load flow solution: the slack power, slack bus power, real as well as reactive, the losses, real as well as reactive, and line flows. Because even in security analysis, which you may be reading somewhere, you will have to see the overloads. The line flows should not be overloaded, line should not be overloaded. If this is not equal to epsilon, less than epsilon, then we evaluate Jacobian again, we find out the correction vector, delta VR and delta R, add it to the earlier one, get new VR plus 1, get new delta R plus 1 and continue. Continue what? Till not till eternity, till these conditions get satisfied, and that is the end of your load flow solution. Now, as I have told you during Gauss-Seidel, in case there are constraints, in life there are constraints, nobody is unconstrained, even Birlas, Tatas or Reliance or Mittal's, they have limited wealth, it is not infinite wealth. Even I have 1 hour class, even your minor is 1 hour or major is, there is a constraint, you have 24 hours in the day, constraint. In life we are always constrained by many things. So similarly here, if voltage crosses the limit, there is a concept of change of bus. Luckily you can either cross the upper limit or lower limit, not both simultaneously. Either you are inside the studio or you are outside the studio, you can't be simultaneously both places, only God is omnipresent. So if it crosses a upper limit or a lower limit, remedy is same, you convert it into the change of type buses, PQ to PV or PV to PQ, depending on Q is crossed or V is crossed. If Q is crossed, PV becomes a PQ bus, you fix that Q and that becomes a PQ bus till you are back within the range, then you can change back. So this is a change of bus type, okay, which can take place, and finally the final solution should be within constraints, otherwise that is not a correct solution, because feasibility is a more important condition than optimality. See, the solution has got to be feasible first and then only you can look for optimum. Of course, there are methods in optimization techniques where you start with optimality and go for feasibility, but eventually you have to attain feasibility, then only you can say the solution is optimal. Kindly solve the example 6.10 of your book and read the flow chart, because certain stereotype universities still ask draw the flow chart, half an hour gone, you know, but it depends on your teacher and class and so on. Certain people can still ask, in engineering services they can still ask. Luckily GATE has become fully objective type, so they can't ask you flow chart in GATE exam. This is all about Newton-Raphson. The flow charts have been given in book for polar version as well as rectangular version. As I told you, there is a plus point in polar, there is a plus point in rectangular. Nothing is absolute, it depends what do you want. Let me tell you also one thing, polar is more realistic because direct voltage, direct angle. What is this E and F? Nothing practical about real part of voltage or reactive. You can't go and catch real part and leave imaginary part in voltage, but it's a numerical convenience. That's why we have gone for E and F. Now next, there are so many load flow methods, starting from Gauss, Gauss-Seidel, Newton-Raphson, approximate load flow which we have done once, where we ignore resistance, so it becomes a, you can get a closed form solution if you want to. Then there is a decoupled load flow which we are going to start soon. Then there is a fast decoupled load flow, then there is a super decoupled load flow like super express and so on. Then there is a second order load flow method, and finally we will have an optimal load flow method. Then we have stochastic load flow, because after all your loads are not known with complete certainty, they are random variables. When you get a phone call, nobody knows, it is a random event. When you get a customer in a shop, is a random event. Nobody knows unless until you have an appointment, like doctors, like lawyers. There also you get 15 minutes this way, that way. The jams, the bus you couldn't get, or you can get the parking and so on. So that's a stochastic load flow. The very first paper in probabilistic load flow came in 1973 by a Polish lady, Borowsko. And since then, stochastic load flow and hybrid load flow and so on. There are varieties of load flows. People have done master's thesis, doctoral thesis on load flow. there is a continuation power flow. That is if you go for contingency analysis and security analysis. Maybe for undergraduate, I do not know, Dr. Mishra will tell us whether it will go up to that extent or not, because you have to do full course. You do not have to do only load flow for the rest of the semester. What is decoupling? The power system, we have a golden principle of decoupling. What is that principle? P is more friendly to delta and Q is more friendly to V. So, like you move in a group. Some of you go together to Priya Cinema or to Chanakya, or you go for a restaurant. So, like a togetherness, affinity. So, similarly the real power is having more affinity towards, I will write here equation which will show you that P is EV by X sin delta. Once transmission line is built, X is fixed. Okay. Of course, if you do some compensation, this and that, minor changes can be there, but again it is fixed, having done compensation. E and V are also fixed, they are supposed to be fixed close to 1 per unit, and hence P is directly proportional to sin delta. And delta, as all of you know, we operate close to 30 degrees in the linear portion of the P delta curve, power angle curve, which you must have done in your stability, if in case you have done it. For our undergraduate friends, you might have not done stability, you will do it perhaps, hopefully in some course. So, delta is small, and all of you know from your trigonometry knowledge that sin delta is small, sin delta is close to delta. Even sin 30 is 0.866, very close to 1. Sorry, so delta, when delta is 0, sin delta is also 0. So, it is close to delta. So, now this is the equation which shows that P is only dependent on delta, not on V. Reverse is true for Q. This is approximate. Otherwise, you can write those 4 big equation. Receiving end Q, sending end Q, receiving end P, sending end P, and so on, those 4 big equations. But when it is approximated, lambda delta goes away. In fact, cosine delta term is there, but delta is small, cosine delta becomes 1, cosine 0 is 1. So, this is proportional to voltage, and that is why my famous decoupling principle is P is close to delta and Q is close to V. Using this, what I have done? Really bad that this here. I can make this off diagonal terms 0. What were these off diagonal terms? Delta P by delta V. Do you recall that? If you go back to Newton-Raphson method, delta P, when P is not dependent on V, where is the question of variation of P with respect to V? So, I am within my right to put it 0. Similarly, I am within my right to put this also 0. Q is not dependent on delta at all. And this has done a miracle. And what is the miracle? Suddenly, off diagonal terms have become 0. And hence, I can decouple these 2 equations as this. And that is why this is called decoupled load flow method. Suddenly the dimension has become half. So, a smaller computer can be used in case you have one. In fact, you can solve real power problem independently of reactive power problem. If you are not interested in economic dispatch or economic operation power system, you are only interested in minimization of losses, solve only reactive power problem. But you are interested in both, then either you can form in a sequential mode or a simultaneous mode. What is sequential? Solve one equation from here, solve one from here, another this like this sequentially. What is simultaneous? Solve them together as if they are one equation. Sequential is better than simultaneous. First solve all delta p so that you get latest deltas, put them equal to here, and then you get a latest solution for v's also. As I just said, sequential is better. It gives you faster convergence. It reduces memory requirement. You need to have that space only, and the next problem can also be solved using the same space. So, you have reduced your memory requirement. Takes more iterations as compared to Newton-Raphson, but reduced memory requirement, reduced computation time per iteration as compared to Newton-Raphson. This question is normally asked in the examination. Compare various load flow methods, especially these three methods: Gauss-Seidel, Newton-Raphson and FDLF. We have not yet done FDLF, so let us first do FDLF, then we come to this comparison. Fast decoupled load flow method. What is the concept in fast decoupled load flow method? We avoid certain computation, so things become faster. What is the biggest bottleneck or problem in Newton-Raphson method or even decoupled load flow method? You have to invert a matrix in each iteration. That takes a lot of your time. Suppose iterations are 10. Normally, since Newton-Raphson has a quadratic convergence, it converges fast in 2 to 3 iterations, right? But even 3 iterations means you have to invert 3 times. Why do that? How do you avoid that? By making Jacobian constant. If you make it constant somehow, the constant matrix, how many times you will iterate? Only once, because the matrix remains the same. There is no point in iterating it again and again. Only a mad fellow will do it, because you are not gaining any new information. The matrix is same, so inversion is also same. And hence, if you can produce a constant Jacobian by physically justifiable assumptions, you can't jabardasti constant. You have to prove, you have to show to the world, look, it is possible. And there are certain conditions which make it possible. Those conditions, of course, we will look in the next class, and I am not going to do it today, but let me tell you, conditions are same. Resistances can be ignored as compared to reactances, or deltas are small. These are the various justifiable assumptions, and G can be ignored as compared to X. That is same thing as R and X. So, we will see what are those conditions. There are more conditions, and this paper came in 74 by Stott, Brian Stott, who used to be in UMIS 10, and that is a milestone paper. One paper can make you immortal, like Domel and Tinney, Newton-Raphson, 67, that paper came in 67. The Gauss-Seidel paper, Ward and Helle, came in 56. That is the first load flow paper. Before that, people used to solve network by AC calculating board or DC calculating board or analog computer. Prior to that, it was only slide rule. I do not know whether your generation has even heard the name of slide rule. I used to carry as a student every day a slide rule, and we had to solve numericals using that, and used to be very approximate. Nowadays, things are so easy. And only one inversion is the benefit of this FDLF. Now, let me give you brief comparison, because our younger friends won't be available next time. The Gauss-Seidel, Newton-Raphson and FDLF, this is easy to understand. This method anybody can understand. Newton-Raphson method is complex. This is slightly less complex because only one inversion is involved. Minimum storage requirement in Gauss-Seidel. In fact, there is no other method which needs which can have lower than this as a storage requirement. Here is a maximum storage. This is 40% less than NR. Third, programming is very easy. Of course, nowadays MATLAB and Pascal and hardly anybody has to do any programming. In our days, we had to carry so many cards, used to punch, one mistake, error, and output will be given next day. You have to wait for 24 hours to correct it. Programming is tough here, less tough. Conversion wise, this is the worst, it has a linear conversion. This is the best, it has a this what you call quadratic conversion, and this is geometric conversion. I have given one appendix on convergence also. So, if you want you can read that. If I am not mistaken, it is nth appendix in this book and some appendix in that book. So, linear, quadratic, geometric. Convergence wise NR is the best. If you want sensitivity property, what is sensitivity? If delta varies, how much P varies? That is the sensitivity property, delta P by delta Q. It is not available here in Gauss-Seidel as there is no derivative involved. You can see, you remember Gauss-Seidel equation, there was no derivative, it was very simple equation, 1 over yi minus pi minus jqi upon yj star in bracket sigma vy and so on. That was the Gauss-Seidel equation. Here we do have a sensitivity property, here we do have a sensitivity property. These are required for optimal operation, optimal load flow, and hence these methods are more suitable if you want optimal load flow. System size, this I am talking about the attributes. You have to make one more column. When you give this table in exam or somewhere, or when you write a book, you do not have to write only 3 columns, you have to, fourth column is attributes, which I am only telling you. Like here I was saying how the method is, here I was saying storage is the attribute, here the programming is the attribute, here the convergence is the attribute, here the sensitivity property is the attribute. Now I am talking system size. If system size is small, then Gauss-Seidel is wonderful, but if it becomes 1000 bus system, then there are problems. But this NR method does not care for system size, it can be any system size. Whereas FDLF, again system size is not that much of a problem. The time increases linearly with system size in Gauss-Seidel, whereas in NR it hardly matters whether it is a 3 bus, 30 bus, 300 bus or 1000 bus, more or less it converges in 3 to 4 iterations. Here it takes 5 to 6 iterations, because convergence is not quadratic but geometric. That is, geometric is in between linear and quadratic. So, this is about system size. Seventh, type of system. If it is a normal system, then Gauss-Seidel is no problem, but if it is a ill conditioned system, then Gauss-Seidel is having a convergence problem, may have a convergence problem. Let me also tell you, some experts feel before doing Newton-Raphson, it is always advisable to have 1 or 2 iterations of Gauss-Seidel, but not necessary. This is just one opinion. Is it, Dr. Mishra, is it proved or it is just an opinion? Huh?
Not yet proved.
Not yet proved. See, so you have an expert opinion also. So, but then certain people have stated this. So, I thought I will as well state.
It may decrease the iteration to some extent.
Yes,
If
that,
you have a
yeah,
starting with Gauss-Seidel.
Gauss-Seidel. So, this is what you should know, that sometimes it helps if you have first a Gauss-Seidel 1 or 2 iterations and then you go for Newton-Raphson. Now, let me tell you, the FDLF, there is some sacrifice in accuracy. After all, you have ignored those off diagonal terms. So, when the attribute becomes accuracy, nothing to beat Newton-Raphson, because you are not ignoring anything in Newton-Raphson. You are taking the system as it is, as it stands, as it exists. Whereas here, for your own benefit, for your own convenience, for your own comfort, you are no doubt you are justifiably ignoring it. But however, the fact remains that it brings in certain amount of approximation and hence certain amount of inaccuracy. So, in case somebody is very particular about accuracy, well, for him or her, Newton-Raphson is the only prescription. I think with this, I thank you and we finish this. Any difficulty if you have, you are most welcome to ask.